In this video, we're going to look at graphing with transforming polynomial functions. Remember, a polynomial function can have a lot of terms, or it can have simply one term. And here's a new word we want to look at, power function. A power function is a function of the form y equals a times x to the b, where a and b are non-zero real numbers. This means pretty much that we have x to a power as our only term. It says cross out the functions that are not power functions. Well, this is a power function because 0.36 times x to the ninth, it's just pretty much x to a power. The second one is not a power function. It has two terms. That's a polynomial function, not a power function. A polynomial function can have one or more terms, but a power function only ever has one. The next one is also not a power function because, again, it has two terms. The last one is a power function. I'm allowed to multiply, and I'm allowed to have x to a power. We want to look at graphing some power functions. We're going to graph y equals x squared, y equals x cubed, y equals x to the fourth, and y equals x to the fifth. This is a new group of parent functions. X squared we've been graphing for a while. That's called a quadratic function. Y equals x cubed we have not graphed before, but that's called a cubic function. Y equals x to the fourth is a quartic function, quarter like 4. And y equals x to the fifth is a quintic function where the prefix quint means 5. I've graphed y equals x squared before. I can plot my table of values. 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. When I square a negative, my answers are still all positive, and then I can plot my points. I want to plot everything that fits on my graph. And then when I connect them, I'm going to connect them with a nice smooth U shape with arrows on each end. This graph has nice symmetry about the y-axis. If I folded it in half right down the middle, it would look the same on both sides. When I go to graph my quartic function, just like with my quadratic, 0 squared is 0. 0 to the fourth is 0. 1 to the fourth is still 1. When I take a negative to an even power, it's going to be positive. So just like my quadratic, I have the same 3 points to start my graph. But when I get to x equals 2, 2 to the fourth is 16, and so it's negative 2. So when I go to plot this next point, it's the only other thing that's going to fit on my piece of graph paper right here. And this is very steep on the edges. It still makes a U shape. It still has arrows on both ends, and it still goes through our beginning points there. 3 to the fourth is 81, and negative 3 to the fourth would also be 81. Again, those aren't going to fit on there. I'm just going to take a brief step to another slide here and look at what overall is happening. If I'm graphing y equals x squared, that's shown in red up here, that's a U shape. Y equals x to the fourth is a U shape. Y equals x to the sixth would make a U shape. X to any even power is going to make some sort of U shape. All of these are going to go through this same initial set of points. 0 to a power is 0, 1 to a power is 1, negative 1 to an even power is 1. So all of these x to an even powers will go through the same spot, but they make a little difference in between. When I look at the values in this space here, the space between negative 1 and 1, if I take a fraction, like if I take 1/2 and I plug in x is a half, if I take a half and square it, it becomes 1/4. So that's this point that I would have plotted right here on my red curve. If I take 1/2 to the fourth power, that's 1/16. which is smaller than 1/4. If I take 1/2 to the 6th power, it's 1/64, which is even smaller. So the bigger my exponent, the flatter my u is. The u looks more square on the bottom than rounded on the bottom. When I look at numbers on the outsides, numbers bigger than 1 or smaller than -1, my graph is going to get steeper when my exponent's bigger. For example, if I take 2 squared, that's 4, but 2 to the 4th is 16, and 2 to the 6th is 64, and that's why the ends of my u are getting steeper and steeper. Okay, so let's go back to my cubic and my quintic now. If I want to plot y equals x cubed, again, 0 cubed is 0, 1 cubed is 1, so my graph starts out pretty similar. But when I cube a negative times a negative times a negative is equal to a negative. So rather than make a U shape, this one's going to be going down on the right. 2 to the 3rd is 8. 2 to the negative 2 to the 3rd is -8. So when I plot this, it makes a little bendy shape. I think this point's off. Yeah, it's actually up there. Sorry about that. Didn't count. Okay. 3 to the 3rd is 27. 3 to the -3rd is -27. Those aren't going to fit on my graph, but that's our shape for our cubic. That's our parent function. The quintic starts out very similar. 0 to the 5th is 0. 1 to the 5th is 1. -1 to the 5th is -1. And it looks like it's going to be starting just like our cubic did. But when we get to the 2 to the 5th is 32. So these points aren't going to fit on our graph. 3 to the 5th is 243. So this thing's shooting way up in the air and way down. And I need to be sure when I'm drawing it that I indicate that. You notice I'm not floating way over here like this. That would be bad. I don't want to do that. I'm staying within my line right there. Same thing over here on the left side. This one's going down. So let's take a general look at my x cubes. X to the 5th, x to the 7th. All of these with odd exponents are all going to make this bendy shape right here. All the ones with odd exponents make a bendy shape. They're all going to go through these same 3 points in the beginning. But again, just like with the quadratic, if I have a bigger exponent, as my exponent's bigger, my graph gets steeper and steeper on the outsides. And on the insides, on this little space here in between, my graph gets flatter and flatter. So a bigger exponent is going to have a flatter graph in the middle, less of a curve shape. Next, we want to look at transforming these graphs. Remember, transformations were when we either moved or we stretched or we flipped, did those kinds of things. So this is transforming y equals x cubed. So this is our parent function, x cubed. And again, that's called a cubic function. We know the cubic function makes that bendy shape. So they ask us, what is the equation of the graph of y equals x cubed under a vertical stretch by a factor of 1? Vertical stretch by the factor of 1. We know that stretches are multiplication. We know that vertical means we need to go on the outside. So if I wanted to fix this equation down here, I would need to put a 1 on the outside to make this a vertical stretch. The next thing they want us to do is to do a horizontal translation of 3 units to the left. We know that translation means move. The way we move is by addition and subtraction. If we're left or right, we need to be inside. and we need to do the opposite of what it would say. So in order to move 3 to the left, we would need to put a plus 3 on the inside. So in my equation, that's going to happen down here. This is my horizontal translation. That's where I move 3 left. So technically what I'm going to do is I'm going to subtract a negative 3. Over here on the right, I would probably write that as a plus 3 instead. Okay. The last thing that we're doing in our equation is we want a vertical translation of 4 units down. A translation means move. Vertical means up and down. And in order to go move down 4, we need to be on the outside for up and down, and we need to subtract 4 to move down 4. So out here on the end of our equation, we're going to need to add a negative 4, or in simplified version, we'd probably just write minus 4 on the end. And this is our vertical translation. All right, and then we do a little summary down here. The graph of the function y equals a times f of x minus h plus k is a vertical stretch or compression by a factor of the absolute value of a. Remember that if a were negative, then that would make a flip. So they're saying to make the absolute value of a tells you how much you stretch it. A horizontal shift of h units, because you're going to move h units to the right, and a vertical shift of k units. So that means you're going to move up k from the original graph of y equals f of x. On number 7, we have a new parent function, y equals x squared, and this is asking us which of these are transformations of x squared. The first one is a transformation of x squared because we're flipping it over with the negative and we're stretching it vertically with the times 7. The next function, y equals 4x cubed plus x squared, is not a transformation. That is a cubic, and it's a polynomial, so we're not dealing with that here. Y equals x squared plus 5 is a transformation. That's a u moved up 5. This one's also a transformation. It's a u shape, moved 3 to the left and down 5. The last one, y equals 2x, is a transformation, but it's a linear. It's a line, so it's a transformation of a line, which means it's not from the same parent function. Question number 8 asks us to graph this function using transformations. So we should know right now that it's a cubed is our parent function, so it's going to make a bendy shape. We know that the minus 4 on the inside is going to move 4 to the right. And we know that the plus 1 outside is going to move us up 1. So when we go to graph this, we're going to have a new anchor point. We're going to move 4 to the right and up 1. And this is where our whole graph is going to start, 4 to the right and up 1. Now I just need to plot my basic shape for an x cubed. So I have 0 cubed is 0, and I'm going to go through that point. My next point would be over 1 and up 1, because 1 cubed is 1. I could also go 1 to the left and down 1 to take into my negative. 2 to the third is 8, so from my anchor point, I'm going to go over 2, up 8. Or I can go 2 to the left, down 8. And that's my basic shape. Sorry, I counted wrong when I plotted, so I just moved that one down a spot. I counted 8 wrong. All right, so I want you to pause the video while you do 9, 10, and 11. Also, reminder that if you want to, you can use your calculator to help you get your points for these. If I wanted to do that, I'm going to go in the graph menu of my calculator. I'm going to type in the problem pretty much just like it's written. So I would have in parentheses x minus 4, that's to the third power, and then a plus 1 on the end. It's important that you think before you graph. You know if this is an x cubed, it should make the bendy shape, which it does. So that's a good sign I typed it right. If I want to get accurate points, I should probably go to my table menu instead and make the table. A lot of the points in the table are going to be much too big to plot. But if I scroll until I can get some nice single digit points, 2, -7. 2, -7 was this point right here. If I counted it out, that's 2 to the right and down 7. The next point on my table was 3, 0. That's that point right there. I can keep scrolling down. And I have 4, 1, 5, 2, and those are the same points that I have plotted on my graph. So pause the video while you try 9 through 11 and then see how you did. On number 9, I had to stretch times 2 vertically because it was multiply on the outside. X to the 4th told me I was my steep U shape, and the -8 moved me down 8. So the only points that really fit on my graph were from my anchor point right here. I had 0, 0, and then I went over 1 up 2 because I doubled vertically. Here are my answers for 10 and 11. Again, you can use your table to help you get your points. If you're typing them into your calculator, be sure I've shown you some ways down here that you can type them in. Be careful by typing 1 divided by 4x or 1 divided by 2x because that's going to put the x on the bottom. So pause the video if you need more time to check. If not, go ahead and do the last 2 and then pause to check those. Okay, here we had x cubed and 4x cubed. So they're the same shape, but the 4x cubed is going to stretch us and make us a little taller. And those are our transformations.